So in today's lesson, we're going to be having a look at the A-level chapter 8, which is Parametric Equations. So this is just a quick overview of the chapter. So 1, we're going to be converting from parametric equation to Cartesian form. We'll talk about that, what that is in a second. 2, we're going to be looking at sketching parametric curves. 3, we're going to be looking at finding points of intersection, and then we're going to be looking at modelling. Now, personally, I actually really like this chapter. This is one of my favourite chapters because I find it really interesting that when things get broken up and you're in a sense adding an extra dimension into what we're doing. And I'm not talking about forwards, backwards, and sides and up and down. I'm talking about an extra dimension in terms of like things like time and what's happening during space-time, which I find really interesting. But you'll see what I mean in a little second. So here we have two types of equations. The first one here is called a Cartesian equation, which is this one here. And this is just how things are represented in terms of x and y. So here we've got a curve, x squared minus y squared is equal to 5. And it comes up with a curve that looks like this. So here we've got two variables. It doesn't have to be two variables. It can be more, but the majority of the times we're looking at Cartesian equation, which is in terms of x and y. And what you do is you use either an x coordinate to generate a y coordinate, or the other way around, we use a y coordinate to generate your x coordinate. Now, the thing which you're going to be looking at today are parametric equations. Okay, now this is, usually I do a little demonstration about throwing things across the classroom and kind of seeing the pen kind of flying. You might be able to see in the corner there flying over. What we're looking at here is how things change in terms of another dimension. Now, the one I always like to think about is time in this case. So I'm just going to snap to full screen view, just so you can have a little look at my, I'm going to use, let's have a little look, this pen it'll do. So, when we're looking at Cartesian equations, imagine if we've got a x and y coordinate here, and we've got this in the centre. So if we were moving in the y coordinate, we'd be moving up and down. If we're moving in the x coordinate, we're going to move in left and right, like so. However, when we're thinking about parametric equations, we're thinking about how the x and y coordinates change with time. So what we're thinking about here, if I think about this moving, let's think about moving like a quadratic. So if I think about throwing this up and then it's coming down here, this follows that kind of U shape, doesn't it? Imagine if I was throwing this up there like so and it'd come back down. So imagine this is the ground and I'm throwing it up there, it's come back down, okay? So when you're thinking about Cartesian, you're thinking about how this pendant changes with respect to time. Sorry, with respect to height and x and y. So vertically and horizontally. But what we're thinking about now is we're thinking about how this changes in terms of time. So what I'm talking about here is let's do it slowly. So let's count in seconds. So how is the x and y changing in terms of kind of 1, 2, 3, 4, 5. So how is that x and y coordinate changing in terms of time? So let's just go back to this one here. So here we've got a different curve, and we've got x is equal to sine t and y is equal to t squared, and we're looking at how these x and coordinates are changing in terms of time. That's like changing. So it still has this pattern. We could still form our equation in terms of this one. However, we're thinking about, as time progresses, where is the x coordinate, or what is the x coordinate and what is the y coordinate? So yeah, that's the starting point. So converting parametric equation to a Cartesian equation. So how could we convert these parametric equations into Cartesian ones? Now, there's a few different ways you can do it. I'm just going to get this part up. Give me 1 second. So Sorry, give me a sec. Super. So let's have a look at this first one here. So the best way to do this is to use substitution to eliminate the parameter. So what do I mean by that? Well, if we've got x in terms of t, which is what we've got here, we've got x in terms of t, and we've got y in terms of t. So what we're saying here is, how do x and y change with respect to time? Now what we can do here is we can simply just substitute in for t to eliminate the parameter that we want. So the first thing we would do with this one is so I'd probably get this one down as example 1. If you've got the booklets, you can use the booklets. If not, then just write it in your notes. So we're going to make t the subject, and we do that really simply, but I just divide it by 2. So t is equal to x over 2, like so. And then we're going to substitute this into that the second equation. So this is equation 1, this is equation 2. And we're going to end up with y is equal to x over 2 all squared, substituting that in. So our Cartesian version of this is going to be y is equal to x squared over 4, like so. Everybody happy with that? Just pop your hand up if you're happy with that. Super. So the next thing we need to think about is what is the domain of a function, what is the range of the function. Now notice with this one here, they've given us here limits to our time, or t in this case, and they've said that t can be -3. Now obviously that can't be time, because well, it could be time if you have a particular point in the future. They've given us limits on what t is, so starting at -3 and going all the way forward to 3. Now we know that our domain are our x coordinates and our range of x coordinates. I shouldn't say range, or the values of the values that the x coordinates can be, and we know that the range is the value of the y coordinates. So if I want to find out what my domain is for our Cartesian form, then we would need to substitute in this here, to substitute in t for our x, values, and that's what they've done here. So they've substituted in here. So if I look at this part down here, they've substituted -3 in and then 3 in. So we have x is equal to 2 times by -3, which is equal to x is equal to -6, and then also we've got x is equal to +3, and it gives us our domain, which is this one here. Now we do need to be really careful with that, because we know that when we're doing things like quadratics, or if we've got a quadratic as an x, it doesn't always work. We can just sub in the highest and lowest value, okay? But with this one it does. In which case, actually, this is exactly what we're talking about here in the range, yeah? So for the range of this, we know that we need to know what the lowest value of y is and what the highest value of y is. If I sub in -3 into both of these, then I get a bit of an issue, don't I? Because if I sub in -3 into y is equal to t squared, so y is equal to minus 3 all squared, it gives me y is equal to 9. However, I know that for y is equal to t squared, this goes all the way down. This looks like, I'll just do a little sketch of it. So y is equal to t squared. If I say that this is y and this is t, then this is what the graph looks like of y is equal to t squared between minus 3 and 3. It starts at 9, it continues to 9, but the minimum point of this is 0, isn't it? Okay? So actually, the range of this is going to be between 0 and 9. Very similar to when we were doing domain and range from functions. Can you just pop your hand up if you are okay with that? Does anybody have any questions on that? If you've got a question, then maybe pop it in the chat. Otherwise, I'm going to move on. Am I okay to move on? Super. If you've got your hand up still, can you just pop it down for me, please? So let's have a look at this question then. A curve has a parameter, sorry, a curve has a parametric equation. A curve has the parameter equations x is equal to log of t plus 3 and y is equal to 1 over t plus 5, where t is greater than minus 2. Find a Cartesian equation of the form y is equal to f of x, where x is greater than k, where k is a constant to be found. We're talking about here the domain of this, and write down the range of f of x. So the first thing we need to do is we're going to need to, first of all, we're going to need to rearrange and substitute in to make this in our Cartesian form. So which one's the best one to rearrange? I would probably rearrange this one here, although you can rearrange the other one. The reason I'm rearranging this one is because we probably want it in the form y is equal to something, because that's what we usually have, and this is already in the form y is equal to something. Okay, that's what we usually have Cartesian. It's usually y is equal to x squared plus 6, or y is equal to 2x minus 3. That's what we usually have. So if I write this one down here, so x is equal to ln of t plus 3. We know that the base of this one is e. So this is the same as saying e to the power of x is equal to t plus 3 using the laws of logs. E is the base, raise the other side to the power, so e to the x is equal to t plus 3. So then t is going to be equal to e to the x minus 3, like so. Then what we need to do is we need to substitute this into, so let's call this one equation 1, call this one equation 2, so sub in to 2. So we're going to have y is equal to 1 over t plus 5. Let's just highlight what we're subbing in. So we're going to have here y is equal to 1 over t is equal to this e to the x minus 3. So e to the x minus 3 plus the 5, which is going to give us our Cartesian equation, which is y is equal to 1 over e to the x plus 2. Now, the issue here is they've asked for this part here, so when x is greater than k. Now, what they're asking for here is they're asking for your domain. That's pretty much what they're asking for. So, it says here, a common strategy for the domain and range is to consider what happens at the boundaries, but you've got to be careful with that. Remember, we can't just consider the boundaries, because when we've got things like that quadratic, however, I know that for ln x, I know that this looks like a graph which is just constantly increasing like so. It's going to look like this. This is what the e to the x graph looks like. We know that the e to the x graph, sorry, ln x, it looks like this. We know that it's constantly increasing, so we can just think about the boundaries for this one here. So let's substitute in our boundary for t, which is equal to this. So when t is greater than -2. So if I substitute in this, sub in, t is equal to -2. 2, because we're dealing with domain, we're going to be subbing it into the yellow highlighted one, which is going to be x is equal to ln of t plus 3. So if I substitute that in, I'm going to get x is equal to ln of -2 plus 3, which is going to give me x is equal to ln of 1. ln of 1 is equal to 0. So therefore, this is going to be when x is greater than 0. And so k, that value of k, which we were trying to find before, is equal to 0. So this part here, x is greater than 0. So we know that k is equal to 0. Just pop your hand up. Is everybody all right with that? Super. Oops. So the next up, we need to think about part B. And part B says, write down the range of f of x. So we know that the range is going to be this blue highlighted part, which is going to be y is equal to 1 over t plus 5. Now the problem with this is the reason they've done it as part B is they're probably going to be thinking about what does this graph look like. Well, we know that the graph of y is equal to 1 over x looks like this. We know that. Oops. So inside bracket opposite, so if I'm adding 5, I need to move left by 5 for this one. So this graph here is going to look like, there's going to be an asymptote instead of at 0 at -5. And it's going to be like this, isn't it? So what happens if I substitute in t is equal to 2 into this? What do I get? So let's sub in t is equal to -2. I end up with y is equal to 1 over y is equal to 1 over -2 plus 5, which is equal to -1/3. Okay, so if I think about what this graph is going to look like, it's going to start at -1/3. Now, if this goes all the way to -5, this one here is going to start here at when y, so this part here, when y, oh no, it's not going to be there. Let's have a little think. So we need to be careful of this graph. So we're starting here when y is equal to a negative third, which is going to be minus 2. Is a positive third. What am I talking about? That's why I'm getting so confused. Thank you. Because it's 1 over 3. Thank you, thank you, thank you. So, yeah, it's a positive third. That makes way more sense, because now when I draw the graph, it starts at a positive third, which is there, and it's going to come down. It's going to go an asymptote to tend towards 0. So this is what the full graph would look like. But actually, we know that we're starting at this point here at a positive third. Thank you for letting me know. And now the important part is that this graph here is actually getting lower, isn't it? Can you see how here this is going down from a third all the way down there? So it's going from a third, it's going down. So we can say that the range is that y is less than 1/3, because it's getting smaller. It's not getting bigger than a third. It's y is less than. The only way we can see that is by looking and thinking about this graph. Does that make sense, everyone? You just pop your hand up if you're happy with that. So the reason that we substitute in the minus 2 is because this is what they're giving us as the range for t. The range for t, sorry, the domain range for t is that t is greater than minus 2. Now remember, this is our limit for t, but our domain is what our domain is are the values which x can be, and your range are the values that y can be. Does that make sense why I'm subbing in minus 2 now? Good, yeah, so super. So, yeah, it's all about making sure you understand that the x-coordinates are the domain and the y-coordinates are the range, and the t is telling us what these are. So let's move on to the next one then. So let's just check that. Brilliant. Yeah, good. Super. So I've got these two questions here. I'm going to say to have a go at this one. In fact, have a go at both yourself. I think you should be able to have a go at both yourself. Have a go at both yourself. If you are catching up with this at home, then maybe pause and have a go at these yourself. I'm just going to wait a second. Now we'll go through them in a second, but have a go at both of these yourself now. So we've had a question about this, which is y is equal to f of x, and what does that mean? So what they're basically saying here is that they want it in the form y is equal to something in terms of x. So what they're pretty much telling you is that they want you to rearrange this one, make t the subject in this one, and then substitute it into this one, so you've got y is equal to something in terms of x. Because at the moment you've got x in terms of t, you've got y in terms of t, but they're asking for y in terms of x, which is the Cartesian equation of this. So I'm going to go through this first one here. So we're going to make t the subject. Let's label them. We're going to make t the subject in this one, so I can sub it into equation 2. So x is equal to ln of t plus 2. So in this case, it's going to be t plus 2 is equal to e to the x. Very similar to the last one we did, isn't it? T is equal to e to the x minus 2. We're going to substitute this into equation 2, which is y is equal to 1 over t is e to the x minus 2 plus the 1. So we end up with y is equal to 1 over e to the x minus 1. So that's the first question done. Just going to highlight it so we know that that's our final answer. And that's 4 marks there. They're not asking us for the... They haven't asked us for the domain and range there. They could have asked us for that. If they haven't asked us for it, I'm not going to go through that now. Find the Cartesian equation for this one. Now this one here doesn't say that it wants it in y is equal to, so you can either make the left hand side equal to or the right hand side equal to, just because we've been doing the left hand side one. So this one here is equation 1, this one here is equation 2. So x is equal to ln of t. So t is equal to e to the x. I'm going to sub that into equation 2, which gives me y is equal to e to the x all squared minus 2. So my Cartesian version of this is e to the 2x minus 2. 3 marks. Nice and straightforward. Everybody happy with that? Pop your hand up if you're happy with that. Brilliant. Super, so that's what we got there, isn't it? And this one here. Brilliant. Okay, so this one here, this is where it kind of gets a little bit trickier. Okay, it does get a little bit trickier now. So what we have to do is we have to start to use trig identities to create Cartesian version of things. So these are the two that we usually use. We usually use sine squared t plus cos squared t is always equal to 1. We know that. But we can also use ones like this, which is that 1 plus tan squared is equal to sec squared t. And what we do is we use these to write things in terms of x and y. So the problem we've got here, so get this one down as example 1, this one here. And the problem we've got here is that we don't like to use, if we were making t the subject in this one here, we'd have to use sine to the minus 1 in this. And then it gets a little bit messy because we've got sine to the minus 1 and then they cancel out somewhere. So instead of using sine to the minus 1 and making t the subject, usually if we're using trig equations, or we've got a parametric equation in terms of sine or cos, then we use trig identities. And I'll show you what I mean by that. So we've got x is equal to just going to write them down again so you know. X is equal to sine of t plus 2. We've got y is equal to cos of t minus 3. Now, we're not making t the subject here. We're going to use a trig equation or a trig identity to substitute in our values to replace sine and cos to create a Cartesian equation. So which out of this one here and this one here has sine and cos in it? Well, we can see that the one on the left, sine squared plus cos squared, is equal to 1. So that's what I'm going to write down. So just before I do that, I'm going to make sine the subject, or sine t the subject. I'm going to make cos t the subject. So I end up with sine of t is equal to x minus 2. And cos of t is equal to y plus 3. Like so. And I'm just going to make it really clear to the examiner. Use sine squared t plus cos squared t is equal to 1 to create Cartesian like so. So I'm going to substitute in now. I'm going to sub in. I know that sine t is equal to x minus 2, and I know that cos t is equal to y plus 3. So I know that I can substitute these into here, because that's sine squared t and cos squared t. So I know that sine squared is equal to x minus 2. So I can say that x minus 2 all squared plus cos squared t, which is y plus 3. So y plus 3, but it's cos squared, so I need to square that, is equal to 1. And there we go. We've actually, this now is the Cartesian version, because we've got an equation in terms of x and y. So the next part here says, hence sketch the curve. Well, what's this going to look like? Well, we know that it's now taking the equation, the form of the equation of a circle. So we can see that this is the equation of a circle, and our centre is actually changing this, hasn't it? So it's going right by 2 and down by 3. So let's draw an axis. Draw an axis there. And in this axis, I need to go right by 2, and down by 3. So your centre is going to be 2, minus 3. And our radius is going to be equal to 1, because it's 1 squared. So it means it's not crossing any lines. So we're going to have a circle that looks like this. It's not a very good circle, but you get the marks for that. It's all about knowing where the centre is and knowing that we're not crossing any x or y axes. Can you just pop your hand up if you're happy with that? Brilliant. So let's have a look at this next question then. A curve is defined by the parametric equation x is equal to sine t and y is equal to sine 2t. Okay. Find a Cartesian equation of the curve in the form y is equal to f of x, where minus k is less than or equal to x, is less than k, stating the values of the constant k. Write down the range of f of x. So we're stepping up quite a bit here. Okay, we're stepping up quite a bit. So the first thing you've got to think about is, what equation do I have which is in the form y is equal to, x is equal to, what equation do I have sine and sine of 2t in? Now, this is where you've got to really know all of your trig identities. So the first thing I'm thinking here is, well, straight away I can see this is sine of 2t. Okay, and that's a problem for me, that is. Because now straight away I'm thinking is, which equations am I using which have got sine 2t in and sine of t in? Well, the only one I can really use here is sine of 2t is equal to, now bear with me a second, sine of t cos of t. So we're kind of there a little bit here, because we've got the sine of 2t in there, and we've got sine t, but the issue we've got there now is the fact that we've got cos t in there. So we've now got to have another formula which links sine and cos, or sine 2t and sine t. Now, what we're going to be using for this one is we're just going to be using sine. This is very common, by the way. Sine squared t plus cos squared t is equal to 1. So if I want to write cos in terms of sine, I'm going to go cos squared t is equal to 1 minus sine squared t. And then cos of t is equal to 1 minus sine squared t, all square rooted. So if you've got something in terms of sine and cos, but you don't know what cos is, you can always write sine in terms of cos or cos in terms of sine using this technique. So now let's start subbing in everything that we know. They want it, notice again, in the form y is equal to f of x, which basically telling me that I want to rearrange this one here and sub it into here because it's y is equal to. So let's write down y is equal to sine of 2t. Now I already know, and I've already thought about the fact that sine of 2t is equal to 2 sine t cos t. So y is equal to 2 sine t cos of t. I know what, I know that sine of t is already equal to x. I know that. But the one that I don't know, well, I do because I've got it over here. I know that the one I'm going to need to focus on is this cos t. Now I know that cos t is equal to, over here, I know that cos t is equal to the square root of 1 minus sine squared t, but we also know that sine squared t or sine of t is equal to x. So I know that cos of t is equal to the square root of 1 minus x squared, because I know that sine is equal to x, sine t is equal to x from this part over here. So we've got this green part, which I'm going to replace for sine. I've got the blue part, which I'm replacing for cos. I've had to use the double angle formula to get two things in terms of sine and cos. So I can say here now that y is equal to 2 sine t is equal to x. Cos t is equal to the square root of 1 minus x squared. So that's our Cartesian equation, this part here. Now I haven't actually finished yet because they're asking for the domain of this. Okay, now our domain is when we've got our x values and what our the values which x can take. So let's substitute in now our limits of t to see what we've got. So when t is equal to minus pi over 2, x is equal to sine of minus pi over 2. Now you're going to have your calculator in radians here. So sine, shift mode, shift setup, radians. So sine of minus shift pi over 2. I mean, we should be able to do that in our head anyway, but I'll just check. That's equal to minus 1. And when t is equal to pi over 2, so the other end of this, we're going to have x is equal to sine of pi over 2. So go back. Pi over 2 is equal to 1. Which makes sense because they're saying it's going to be minus k and positive k. So these two values are the same, so it's going to be minus 1, which makes sense because this one here is minus 1, sorry. And this one here is positive 1. So our domain for this is minus 1 is less than or equal to x is less than or equal to 1. And we can even just make it really clear for, therefore, k is equal to minus 1. So that's part A. Part A is a little bit trickier. It means that we've got to actually think about what we're doing here. Just got to think about what we're doing a little bit more for part B. So for part B, write down the range of f of x. So when we're thinking about the range, we're thinking about our y value. So y is equal to sine of 2t. Now, sine of 2t, what does sine of 2t look like between minus a half and a positive half? Well, we know that sine looks like this, don't we? Sine of 2t, let's even do sine of 2t. The graph looks like this. If it's 2, it's going to be half, so it's going to be between that and 180. Between this and minus, it actually goes minus, doesn't it? So there, like so. This is what that graph looks like. So what is the range of y is equal to sine of 2t? Well, the range is going to be the y values of this, which are going to be positive 1 and minus 1, because it's the sine graph. So your range, I mean, we can sub in these values, but I think it's worth thinking about what that graph looks like. The range is minus 1 is less than or equal to y is less than or equal to 1. Because this is what the range of this is. I mean, I suppose we could have done that for sine of t as well. When we did this part, thinking about what y is equal to sine of t looks like. Between the two values which we've got, which are this. Tricky question, but we're getting into it now. Let's just check then. Here we've got our circle, there's our Cartesian, there's our circle. We've got this one here, which is our Cartesian, thinking about changing this part and this part here. We've then got our range, sorry, domain, which is this, and the range, which is this. They haven't drawn the graph, but I think it's definitely worth drawing the graph. That's why. Okay, just pop your hand up. Everybody happy with that? I have to say, I do like this topic. It's one of my faves, I think. I think we're starting to get really juicy into, like, we're starting to use those trig identities. We're starting to think about Cartesian. We're starting to think about the paths which things take, and so bringing in mechanics and stuff like this. I do get quite excited by these. All right, here's a test your understanding. So have a go at this one yourself. It is tricky. The first thing I'm going to say is watch out for this, cos of 2t. What are your trig identities for cos of 2t? Where have I put that? That's what I was looking for. So you should have this. Your Bickham Maths formula sheets. Should be looking at cos 2 theta. Okay. So, we'll come to a natural end there of this lesson. If you are watching this at home, I've just realised that I've muted for a lot of that. I think from this section on, I may have been muted. But you can still catch the notes. I think from this section here, which is probably the hardest bit. So if you are catching up, just be aware of that. You can still follow it. So I'm drawing on here. Right, do make sure you're having a go at the exercises at home if you're catching up. And I'm just going to